Math 1314, Tyler Junior College, Section 3.5, Rational Functions. Graphing via the 7-step approach. Disclaimer, the 7-step approach is not what you would call industry standard. It just depends upon the textbook that you're using or the professor who is teaching you how to graph rational functions. And in case you're wondering which textbook I'm using, not that I'm promoting any particular textbook, it's College Algebra by Blitzer. I forgot his first name. Robert Blitzer. So using Robert Blitzer's 7-step approach, which is the same 7-step approach that I would use, I could probably find more steps if I wanted to. We're going to graph f of x equals 2x minus 1 over x minus 1. Now what are these 7 steps we're referring to? Well, they're things that we've already done. Step number 1 is to determine if the function is even or odd, implying whether it has y-axis symmetry or origin symmetry. Remember, the benefit to having a symmetry is you technically only have to figure out half the graph and either fold or rotate to get the other half. Steps 2 and 3 are just finding intercepts. The x-intercept has some issues, but it has to do with vertical asymptotes and holes in graphs, as you'll see here. Not in this example, but in future examples. So find the vertical asymptote in any holes, find a horizontal asymptote if there is one, find some other points, and I'll show you how to know which other points to find, and then put it all together to draw a graph. So it's not nearly as bad as it seems, it's just a lot of mostly little steps. Let's start with the symmetries. Recall that a function is even if f of x equals f of negative x, and a function is odd if f of x equals the negative of f of negative x. Which, by the way, is not the standard definition by some professors' opinions, but it is equivalent. Both my definition of odd and the alternative definition are saying the same things. To do this, recall to figure this out, we first evaluate f of negative x and compare it to the original. So let's start with substituting a negative into the function. And let's do it efficiently. If I do 2 times negative x, I get negative 2x. That's followed by minus 1. In the denominator, if I put a negative x here, I get negative x minus 1. Now, is this the original function? Not quite. But, and here's where you got to be careful. You can change the look of a rational function or a fraction in general by multiplying both sides of by any non-zero value that you'd like. So I could change this. The question is, can I change it back to the original? Well, no, and here's why. If I wanted to make it look like the original, I need to start with 2x and an x. And I can fix that, or I can try to fix it, by multiplying both sides by negative 1. But will that restore it back to the original? No. It'll restore the 2x and the x, but then it'll mess up the signs on the 1's. So in an attempt to make it look like the original, it would fail. So there's no need to actually execute it. This is not equal to the original, which means it's not even. And remember that even functions have y-axis symmetry, and odd functions have origin symmetry. So we can go ahead and dismiss that this has no y-axis symmetry, but it's not over yet because we also have to compare the original to the opposite of f of negative x. So what's the opposite of f of negative x? Well, that's just sticking a negative in front of the previous one. Again, can we make this look like the original function? Well, first we got to do something with this negative, because the original doesn't have one in front. If you have a negative in front of a fraction, you can either put it on the top and distribute or put it on the bottom and distribute. Let's just say that we choose to put it on the bottom and distribute. We get negative 2x minus 1 on the top, but we get x plus 1 on the bottom. And at this point, there's no way I can restore this back to the original. The denominator has x plus 1. This one has x minus 1. The x is correct, but the 1 isn't. So doing any multiplying to fix the 1 will mess up the x. This is not equal to the original function, which means that this does not have It's not an odd function, which means it does not have origin symmetry either. I'll be honest, most of these don't have a symmetry. There are some exceptions, but in general they don't. So, none. Well, no y-axis or origin symmetry. This graph does have a symmetry. If I remember at the end, I'll show you what it is. Y-intercept. Oh, y-intercept is easy. Just substitute 0. Let's not beat around the bush. If I substitute 0, I'll get 2 times 0 minus 1 on top, so minus 1 on top. 0 minus 1 on the bottom, so negative 1 on the bottom. Basically, putting in 0 kills everything except the constant terms, and negative 1 over negative 1 is 1. So we have a y-intercept at 0, 1. X-intercepts. The story for that is still the same. Solve the function equal to 0. If we want to solve 2x minus 1 over x minus 1 is equal to 0, the first thing we should be concerned about is the fraction, but we've dealt with this before. To solve an equation containing a fraction, it's a good idea to get rid of the fraction as soon as possible, and you can do that by multiplying both sides by the denominator. X minus 1 and x minus 1. The denominators would cancel, leaving you 2x minus 1, but on the right side, 0 times anything is 0. If you look at the big picture to find the x-intercepts, you're really just solving the numerator equal to 0. Solve this and get x equals 1/2. So our x-intercept is at 1/2, 0. And that is the only x-intercept. Next, vertical asymptotes and holes. Recall that finding vertical asymptotes is technically a 3-step process, but sometimes it's a 1-step process. For the vertical asymptotes, you start by solving the denominator equal to 0. That gives us x equals 1. Your next step is to try to factor and reduce, but this will not factor and reduce. So it is its own reduced function. Will this make the reduced function undefined? Sure, because it makes the original function undefined, and it didn't reduce any. So if you have a function that won't reduce, whatever you find here will be a vertical asymptote. Vertical asymptote is x equals 1. There are no holes, because there are no values that make the function undefined, but its reduced version defined, because its reduced version is itself. Horizontal asymptotes. This is where we analyze the degrees. The numerator has a degree of 1, as does the denominator. And when the degrees are the same, the horizontal asymptote is y equals the ratio of leading coefficients. Since the degrees are equal, the horizontal asymptote will be 2 over 1, or y equals 2 over 1. So our horizontal asymptote is y equals 2. Okay, that wasn't too bad. But is this enough information? At this point, I would sketch everything that I know. I know there's a y-intercept at 0, 1, so I can put a dot there. I know there's an x-intercept at 1/2, 0, so I can put a dot here. I know there's a vertical asymptote at x equals 1. And I know there's a horizontal asymptote at y equals 2. Is this enough? Technically it is, but we're looking for branches around each side of the vertical asymptotes. We need a branch on the left and we need a branch on the right. On the left side, I see 2 points here, and I know I'm going to connect them, and I know I have to work around the asymptotes. So I'm thinking the left branch is down here, but I would like some more evidence. And I have 0 evidence of whether the right branch is up here or down here. That's not entirely true. This 6th step about other points is namely getting more evidence to the location of the graph. If you are working a question like this in an online homework platform, it should tell you which x values to use to generate your points. If you're doing this by hand without the guidance of put these x's in, here's how you make your selections. There are 3 x's that I know about already on this graph. I know what happens at x equals 0, I know what happens at x equals 1/2, and I know what happens at x equals 1. Normally what I would recommend is picking x values around and between the ones that you already know. These x values are so close to each other, it's not impossible I can pick 1/4 and 3/4, but I don't think I really need much more evidence here. I need evidence to the right, to the left, and I need evidence to the right. So for evidence to the left, I need to pick a number to the left of 0. Why not -2? And let's put that into the function. -2 on top would give us 2 times -2, which is -4. -4 minus 1 is -5. -2 on the bottom gives us -2 minus 1, which is -3. So we get -5 over -3. The two negatives cancel, and we get 5/3. Because we're plotting this on a graph, it would be a good idea to get a rough decimal approximation. This is about 1.7. So back 2, up 1.7. Back 2, up 1.7 is about there. Remember, this line is y equals 2. At this point, I feel confident enough that I can just connect these 3 dots and work around the asymptotes. And now, I need evidence to see what happens on the other side of the vertical asymptote. So I need to know things about x to the right of 1. Let's get a couple of points. Let's pick 2 and let's pick 3. 2 and 3. If I put 2 into the function, that's easy. 2 times 2 is 4, 4 minus 1 is 3, the top is 3. If I put 2 here, 2 minus 1 is 1, and 3 over 1 is 3. So 2 comma 3 is a point. If I put in 3 on the top, I get, don't know why I'm capping these off, I'm about to use them again. If I put 3 into the top, I get 2 times 3 is 6, 6 minus 1 is 5, so we have 5 on top. And if I put 3 on the bottom, I get 3 minus 1 is 2. So I get 5 over 2, and that won't reduce. But I can turn it into 2.5. So over 3 up 2.5. And now I have plenty of evidence to say, look, here's the rest of it. And I just did step 7 through the graph. So it's really a bunch of little steps. It just kind of drags it out some. One last comment. I said that this graph has no symmetries, but that's a lie. It does not have y-axis symmetry, nor does it have origin symmetry, but it does have a rotational symmetry. Not rotating around the origin, but rotating around the intersection point of the asymptotes. In other words, if I rotated this branch around here, it would land on the other one. Many rational functions do have some sort of rotational or y-axis symmetry. There are ones that don't, but this is one that does. In the next video, we're going to take a look at another example of a graph that requires a little bit more work, but really doesn't take that much more time.